Hey everybody, so today we're going to learn about two more trends. So last time we learned about atomic radius and ionization energy. Same thing with the two trends we're learning today. Try to connect them back to the common theme of how positive and negative things, or the positive and negative force between the protons and the electrons, are what affect all of these patterns. Okay? All right, so the next trend here is called electronegativity. Now, by definition, what this is it's the attraction of an atom for electrons shared in a bond. Key word here that we need to understand is we're talking about electrons that are being shared. So, with these electrons that are being shared, what's important to recognize is that when atoms share electrons, the sharing is not always equal, right? So, for example, just like if your mom says, hey, share this cookie with your brother, you break the cookie, it doesn't break equally in half. And of course, because you're the nice person, you give your brother the bigger piece, right? You still shared with them, but it's not shared equally. So what we're looking at here, let's see if I can draw a picture, is so when two atoms bond, so here's a nucleus, ignore my weird finger pictures that I have to draw here. Okay, here's our atom, here's our rings. When two atoms bond, what happens is their rings overlap with each other to share those electrons. Okay, so what electronegativity is referring to is the force of attraction that it feels as it's sharing that electron. So it's kind of like a tug of war idea. And then the atom with the higher electronegativity is going to draw the electrons towards it. So for example, in this one, we'll talk about why, but fluorine has a higher electronegativity. So that's what this arrow is representing, is that the electrons are being pulled towards, are being pulled towards the fluorine atom. Okay, so we look here at this chart. The bigger the section of blue, the greater the electronegativity is. So if we look at our trends here, we can see that as I go to the right on the periodic table, electronegativity is increasing, generally speaking. So what I'd like you to do is have the substitute pause the video right now and turn to your table buddy and tell them why you think that is. Why would fluorine, that's what this box would be, why is fluorine better at the tug of war than lithium over here? So pause the video and answer that question. Okay, so our reason why of this trend, so make sure you write this why down on your notes, is, hopefully this is what you discussed with your table buddy, the fluorine, or the ones on the right side of the periodic table, the ones over here have that greater attractive force. So when they're having a tug of war, the one with the greater the attractive force is going to win in the tug of war, so it has a higher electronegativity value. Okay? Now, if we look in a group, which means up and down, the trend goes such that it goes up. As I go upward in a family, electronegativity also increases. Our reason here is due to the fact, once again, based on attractiveness, but also because of their size, since fluorine only has two rings that it has to reach out to, versus like iodine down here, it's able to pull those shared electrons a lot tighter than iodine, which has, what, 1, 2, 3, 4, 5, 6 rings on it, 5 rings on it. That would cause it to make it difficult for it to pull on the electrons that are being shared. So ionization or electronegativity actually has the same pattern as ionization energy. Now, you may have noticed looking at this that there are a few X's that are kind of interesting, particularly if you look right here, our top 3 noble gases don't have electronegativity values. It's not that it's 0, it just doesn't even exist. The reason that is keep in mind electronegativity is about the electrons being shared. Since these three atoms never form bonds, they never share, and if they don't share, they can't have electronegativity values. Okay, so the top three noble gases are what we call inert gases because they don't ever react, and so they don't form bonds. And if you don't form bonds, then your electronegativities are just 0. So on our table, what we would say is fluorine actually has the greatest electronegativity of the whole periodic table. So in the tug-of-war battle, fluorine always wins the tug-of-war. And if you're thinking francium as the opposite, that is correct. Francium is always the lowest in the tug-of-war, meaning francium always loses. It always gives up its electron. Okay, substitute once again. If you go ahead and pause the video, students, just find somewhere on your notes and answer these 3 questions, and you can have a smiley face for each one you get correct. Once everyone has a chance to answer the video, or answer these questions, then you can continue on with the video. All right, so looking at number 6, which element has the greatest electronegativity? You'd want to find each of these 4 elements on the periodic table, and after doing so, you should have identified that fluorine has the greatest electronegativity of them all. The element that has the least electronegativity would be our sodium atom because it's the farthest to the left. And then true or false, there is no electronegativity value for helium. True statement, once again, because electronegativity can't be measured for atoms that do not bond. So you can have one smiley face for each of those questions that you got correct. All right, the last trend we're going to talk about today, and we'll do in a demonstration next time, is reactivity. So reactivity is the tendency of a substance to undergo a chemical reaction, either by itself or with other materials, and releasing energy in the process. In general, reactivity increases as elements get closer to a stable full octet configuration. So keep in mind that it's all about getting a full valence shell. That's what this means right here when it says full octet. Okay, atoms react to get a full valence. That's once again why the noble gases don't react, because they already have a full valence. So atoms are going to do what they need to, either take electrons or give electrons to become like the noble gases. So with this trend, it's actually interesting. It's a two-way trend where we have to look at the metals and the non-metals separately. For the metals, it's based on the ability of the element's willingness to lose its valence electrons. Because if a metal loses enough electrons, in a sense, let's draw a picture here. Right, so if we have a sodium, so sodium has 3 rings of electrons. On its valence shell, though, it just has 1, and then its inner shell would be full of 8. 1, 2, 3, 4, 5, 6, 7, 8. And this one would have 2. Okay? So for sodium, to get a full shell, it's much easier for it to just give this one away somewhere than to try to find 7 more. So metals are all about wanting to lose their electrons. And the better they are at losing, or the easier it loses it, the more reactive it is. So what we see for the metals is it increases down and to the left because ionization energy is getting lower. And once again, ionization energy is the energy it takes to remove an electron. For nonmetals on the other side already have a lot of valence electrons, so they don't want to lose. They want to try to gain electrons, right? So for example, like, let's do fluorine. So fluorine has 2 rings, and it has 7, 2, 3, 4, 5, 6, 7 on its outside shell. So what fluorine is trying to do is get 1 more electron. If it gets 1 more, then it gets its 8, making it stable. So for electrons, it's all about this ability to want to gain electrons. They don't want to lose them, they want to keep them. And so we're looking now for this high ionization energy. So for the nonmetals, the trend goes in the other direction, where it increases. So if we put these two trends together, what you get, once again, well, first off, keep in mind the noble gases aren't reactive. They kind of just fall off this trend. But we get a two-way arrow. So you kind of have to split the periodic table at the staircase, right? And things this way are reactive and things that way are reactive. So if you put that together, a reaction between fluorine and francium, well, cesium. Francium's really hard to find. That's why it's in white. But cesium would be an extremely quick and energetic reaction because of where they're both located.